Okay. Hopefully this filming goes better than the first one I did this morning with the AP Chemistry kids. Not my best work. Thought I was focused. I wasn't. Anyway, so hopefully this goes better. All right, so this is going to be kind of this last kind of lab where we kind of tie together a bunch of things. So this is kind of going to go old school. And it's kind of cool because we're going to tie together some kind of random things that we learned throughout the year, and we're trying to figure out why they work. So here I've got yonder really strong magnet. Okay, yeah, you all know about the strength of this. So I put this in here, and these are these sheets of aluminum. So if I drag this here, okay, so I can make this thing move, right, without actually touching it. And more importantly, if I hold it and give that a push, that it acts as a brake. And no matter which way I go, it always acts to slow this thing down. Because if it's not there, I give it a push, oddly enough, it keeps going. But if I put this magnet in here, it acts as a braking mechanism. So now we're going to figure out, number one, just how much that force is. And then we're also going to try and figure out exactly why it works. So in terms of the lab, and I'm going to give you all the data. So we need the weight of this cart, okay? Just took a Newton scale, hung it up, it was like 9.25 newtons. So that was the total weight of this, so we need the mass. I'm going to give you the angle of the inclined plane, so you can calculate your force parallel. Remember FG sine theta, okay? And then what we're going to do is that I'll do this and I'll just give you the data. What we're going to do is we're going to put this up here, and we're going to do sets of trials, where we're going to put it here at, say, 80, and then we're going to let it go down to 40. And I want to time how long that takes. So here's what's going to be important. We're going to know the initial velocity is 0. I'm going to give you the displacement, how far it goes, and then I'm also going to give you the time. So then what you're going to do is you're going to calculate an acceleration without the magnet. Okay, so it's going to be here, we're going to let it go, certain distance, we're going to time it, give you that, we're going to do 5 trials, we'll take the average. Got that. Now, then, after that, then I'm going to take this magnet and we're going to put it up here like so. And then we'll run this again. But then now we'll do the exact same thing. Hold on. Or hopefully it doesn't scrape the sides. Okay, so we're going to let it go through. There we go. Okay, so then we're going to run it a second time with the magnet in there. And what you'll see is that the times are going to be a little bit less. So if what's going to happen is that we're going to know the force parallel trying to drag it down. We're going to know the new acceleration with the magnet in there, which is, and that time is going to be less, so our acceleration is going to be less. And then that's what's going to allow us to calculate the force that's acting to oppose that. So remember, this is all about force net equaling force parallel plus this opposing force. And remember that net force is the only one that equals mass times acceleration. So you're going to know the weight of the cart. You're going to be able to calculate the acceleration of the cart without the magnet. You're going to be able, and we're going to assume that it's initially frictionless. I'm going to calculate a force parallel. And then we're going to compare that to the accelerations when the magnet here is in there and acting as an opposing force. So now let's look at the theory behind it, on why it works. So, let me move that so y'all aren't distracted. And yeah, you can see the board. Okay. So, here's what we've got. So I'm going to assume that this is the north end of the magnet, and this magnetic field is coming out, okay? So I've got, this is what this dots are representing, like this magnetic field is coming out of the page, okay? So magnetic field is coming out of the page, it's coming out like this, not in, it's coming out. So then, when this starts to go through, we're going to assume that, imagine, and this will make sense when you look at the questions. I'm going to assume that there's a little bit of a wire right there, okay? Like, we're going to treat this as a whole bunch of little wires in here that are capable of conducting electricity. So, I'm going to redraw this where we're already in it, okay? So we're like this, okay? And we're going to assume that here's this piece of wire, okay? So as this piece of wire passes this point, it's going to sense an increase in the number of dots, okay? So when this line gets over here, so I'm going to move this over here. So now we've slid down. So this region here is sensing an increase in dots. So to counteract that, it goes, ooh, we need to produce X's. Okay, right. So then, to produce X's, so actually let me draw that over here again. So as that current, as that goes through, it's going to sense an increase in dots. It's going to make X's, so we'll put some X's over here, okay? Because that's what's got to do, that when it passes that, it's got to make those X's. I just drew it over here so it wasn't confusing, you were seeing it over there. So if you use the right-hand rule, the only way to produce X's is if this line, you put your thumb up, and it's going to curl in, so we're producing X's over here. So as that happens, our current is going upward, okay? So that's the direction of my current. So if my current is going this way, and this magnetic field from the magnet is going out. So if I do the right-hand rule, okay, put my thumb up, because that's the direction of the current to produce those X's. So I got my thumb going up, I got my magnetic field going up, or going out. That means my force is going in this direction. So as that force is going in this direction, that's opposing that downward pull of gravity on that force parallel. So even though it's solid, we're going to treat it as like an infinite number of like small little wires. Each one of those is sensing an increase in dots. It produces X's. That current goes up. You use the right-hand rule again. Put your fingers up like this. Point them out. The force is acting upward. That's an opposing force to the downward pull of gravity. So that's kind of the theory. I will send out the lab and give you all the data. The lab itself won't take too long. So that's the story. And actually, yeah, I'm doing a physics lab in a chemistry lab. So it's okay. It'll be all right. So anyway, that's the story, kids.